Hi, hello everyone. I'm Raghuttam. I am from University of Manchester, doing a PhD there. And today I'll be talking on evaluating RFI algorithms for single pulse search. I'm from V and want to come up, some of my teammates are here as well, Kaustav and Prabhu. So we have submitted this paper to RASTI and it's under review. Hopefully we'll be publishing it soon. So yeah, just to give a motivation of what the work is on, etc. So the motivation for the whole experiment was, the observed signal, we hope it's just noise and astronomical source. So it's easy to find the pulse itself, but then there's not the case. So the observed signal will be sum of astronomical source, thermal noise from instrument or other backgrounds, and RFI. So when we search for faint transient signals, the RFI could lead to either very large number of false positives, report inaccurate parameters, and also sometimes like completely obscure the signal, like here you can't see the pulse. Or it can do everything of all of the above basically. So RFI can be treated at various stages, like right from anywhere in the signal chain by restricting the number of RFI sources, or like any other methods that are talked before, like in incoherent beam subtraction. But then today we are basically focusing on post-correlation techniques, that's after beam forming the data. So there are already many existing algorithms such as sum thresholding, or spectral kurtosis filter, or interquartile range mitigation method, or zero-DM match filtering. So all of these focus on different kinds of RFI aspects, and they try to mitigate it. And there are many more. There are many more coming on using machine learning, using all sorts of other statistics, basically. But which one works best? But why does this question come, which one works best? Let's just try and see which one works best, right? But then there are some problems in real-time pipelines that are being deployed now. That includes the real-time pipelines do not give a chance to reprocess the data. So once a run is through and it's gone. So we just have some metadata after that. So you have been listening to all talks this morning, probably even last week. So we don't have chance to reprocess the data. And so for this experiment, we are specifically focusing on simulated data because the real observational data have many things which are not in our control, like contributions from sky, instrument response, RFI, or probably even pineapple fields right beside the telescopes. So in this, the question becomes the detectability of the pulse that needed to be tested. So hence, we ended up running single pulse searches. Okay. So we have developed a method to evaluate how good any RFI algorithm is, at least to our use cases, and in a controlled environment. So we do this using something called test vectors. So how do we generate test vectors? Test vectors are nothing but the filter bank files. They look something like this. You have time in x-axis and frequency in y. It's basically a heat map with greens and blues showing the intensity. So you can see a faint pulse here, noise. So you have Gaussian noise, and then to that we inject a pulse. A pulse might have many different parameters, and also we have some snippets of RFI. So these RFI here might look really systematic, and there are also a few components that we try to include, such as this, and these are from probably satellite passing across, and then these are broadband, short RFI instances like you get from lightning or something, and we have some narrowband as well. So the dimensionality of the problem is such. So any pulse can have different DMs, different widths, different signal to noise ratios, and an infinite number of RFI instances. So we try to break down everything in terms of how much we can. So we can break down RFIs as periodic narrowband or narrowband constant RFI, and we have periodic broadband and periodic constant. This is broadband constant. So we don't consider broadband constant as a different entity right now, because we try to encapsulate all the characteristics in a constant broadband RFI as short periodic RFIs as well, because that's how our algorithm works. So we generate 3 kinds of test vectors. The first set looks something like this. It has kind of realistic scenarios. And the second set is just pure noise. It don't have any RFI. And the third set would look something like this. It has just broadband RFI. And we have another set which has just narrowband periodic RFI, spread all across, affecting around 25% of a band. So as for RFI mitigation algorithm themselves, we have IQRM and SKF, which are implemented on per channel statistics basis. So it treats every individual channel. It takes statistic measures of them, like in moments, and then also try to flag if they are RFI affected or not. And the second one is ZDMF filtering. It stands for zero DM matched filtering. And it works on an entire block of data. It doesn't mask any particular channels, but then work on a complete TF block, a time frequency block. So just for example, if we pass this filter bank across all the 3 RFI mitigation algorithms, we get something like this. So you see the top one is cleaned using IQRM, bottom one, the middle one is from SKF, and the bottom one using ZDMF. Just to focus a bit more on them, so you have something like this for IQRM and SKF, where you basically flag every few channels depending on where the RFI is. And for ZDMF, you can't get rid of these short instances of RFI which have only spread across few frequency bands. So yeah, continuing the pipeline that we used. So we searched the data for single pulses using a pipeline called Cheetah. It basically redisperses the data and then does something called boxcar filtering that we did last week, and then does clustering and sifting. So for clustering and sifting, please refer to the next talk that's coming up by Shubham. He's going to talk about these techniques. I have used something called Friends of Friends. So yeah, so in order to validate when we pass something through single pulse search pipeline, is that exactly the pulse that we injected or not? We use something called protests if it doesn't find any pulse, basically. So protest is a product testing framework to ensure that the behavior of pipeline is right. So it knows the pulse parameters of every pulse, and then it applies some kind of thresholds based on the pulse parameters and try to see if that's the exact pulse that was injected. So we have example, we have like arrival time, dispersion measure, and width of pulse. So example, something like this would be right because it's de-dispersed at right DM, and this would be wrong. And same with the boxcar filtering. So if the matched boxcar is right or not. So for results, I think exactly I'm on time. For results, so after running 3,360 minutes of data, or like say 20,000 pulses. So we have 3 different sets. So we have 3 different kinds of results. So the set 1, we used IQRM only, IQRM and ZDMF, SKF at ZDMF, so that we have good coverage of broadband and narrowband RFI removal algorithms. And we got something like this. So it might take a while to explain this. So you see the y-axis is DMs and the x-axis is fraction of recovered pulses. So if we inject 6 pulses, we expect 6 pulses back. And this is just the fraction of them. So for in case of say strong RFI, which we have all broadband, narrowband, and periodic RFIs, we get nothing when we just clean using IQRM. And we get some of them when we have very weak RFI. When using zero DM match filtering, it's also called Z dot, we get mostly everything back in both the cases whenever we use SKF and ZDMF. But you can see there's some kind of a pattern that all of these follows. That means whenever z dot is applied, you're going to lose some of them, and it's very systematic. Just to evaluate, just to investigate what's happening, we try to do something on the second set of test vectors, which contain known RFI, just noise and pulse. So we cleaned that using ZEMF as well, and then we found something like this. So these are 4 different widths of the pulse, and then based on the widths that we have the fraction of recovered pulses again. So this effect of losing pulses was also discussed in the original paper that was that introduced 0 DM match filtering, and that happens due to subtraction of mean across the time samples. So any pulse that you pass it through ZDMF or 0 DM match filtering, you get these bars which are like dips in the time series, and which also reduces the amplitude of the pulse. And this depends on the width of the pulse as well. More the width, more would be these dips, and then lesser would be the signal to noise ratio that you're going to get for the pulse. Hence, you'll start losing pulses. So yeah, when we did the same thing for even test vectors containing broadband RFI, we lost many pulses, and it was something similar. This is an observation. And for narrowband RFI, so we had test vectors that contain only narrowband RFI, and then which of different strengths, basically 2 sigma, 3 sigma, and half sigmas. And then when we cleaned them using SKF and IQRM, we had something like this as recovery. So the right side is IQRM and left side is SKF. So SKF consistently did not recover this 0.5 sigma pulse. And there was supposed to be some reason behind it. So the only difference between these both, in some sense, were the metrics that they were using. So we tried, and since IQRM has a capability of using any moment or metric that you give it to use, so we tried to clean the same test vectors using different metrics and force IQRM to use that kind of metric. So we use 3 metrics that's called ACF1, kurtosis, and skewness. So when we use ACF1, everything is clean, everything recovers back, because ACF is something called autocorrelation function with a single sample lag. That means you assume that 2 samples that has RFI are correlated in some sense, and noise is not. And if you use kurtosis, we still miss some of them, and skewness, we miss some of them. So the conclusion was, if the RFI is really faint, if the strength of RFI is really low, the skewness and kurtosis are not the best metrics to use, because they don't produce so much variability in the baseband that tries to flag the RFI. So yeah, choosing a best spectral metric makes a huge difference. So what next? So we have new RFI algorithms coming up that are designed, and that needs to be tested. And also, we need to look at number of false positives coming out of these pipelines. The same technique can also be used for periodicity searches. We're just doing single pulse search right now, and also look at effect of baseline variations, because they might also affect the number of candidates coming out of both, even single pulse as well as periodicity search, and also evaluate how good algorithms are doing on them. And then in the era of machine learning, for single pulse searches, there are already a lot of techniques that are introduced. And maybe we can use this kind of test to cover all the corner cases that we want. So yeah, here is the conclusion. So we have developed this method and can be used to test any kind of post-correlation beamform data. And we have tested 3 algorithms, and IQRM and ZDMF seems to be the best one, given that we would still lose some pulses due to the effect of ZDMF. And yeah, thank you.
Thanks, Raghu. Questions for the speaker? So I wanted to ask while injecting the pulses, what was the SNR range of the pulses? And does the RFI rejection, both the algorithms, how does they perform for the high SNR candidates?
Yeah, so the SNR we started to choose from right from 9 sigma till we went on till 182 sigmas. And the difference was not, there was actually no difference between any of them. So since we are flagging at the max till 25% of the bands, even the 9 sigma ones are detected back. And also, since 182 sigma seems to be a lot, but then when spread across 4096 channels, it still becomes less, and RFI algorithms do not flag them. So yeah.
So apart from the SNR, if you vary the DM and width also, so how does that matter there?
Yeah, so it's just trying to cover all the parameter space.
Yes.
So we had.
You said SNR didn't matter, but so do the width of the pulse or the DM matters in this?
No, I mean, I didn't say SNR didn't matter. So it means that SNR does matter because, ultimately you're detecting the pulse with some SNR, and the pulse should not be vanished. But it's a 3D. It's not just 3D. It's like 7D parameter space that we try to cover, and then we had multiple samplings of DM, width, and SNR. And these results that you see are across all of them. So the plots that you had were like for different widths and different DMs in x-axis, and then fraction of recovery in the y-axis. So it does take account into width and DM.
Really nice talk. I was wondering if you are thinking about extensions of your work to more realistic FRB, I guess like pulses and also pulse morphologies, and also I guess the RFI itself, like if you have data from, let's say, airplane RFI or something else that you could just inject over there.
Yeah, so the paper that we wanted to focus on, we willingly not used those real observation data because, as I said, we don't have control. At that point, we'll not have control over everything. Like we can't challengingly place the RFI where we want or such things like that. And also not have control over all the process that are happening, like, modulations of, and then also red noise, all of these things. So in order to test a pipeline, I think that's the best idea to use. We have observation data, and then we inject pulse and cover like a 3D parameter space and do. Especially for what we wanted, we didn't think that was the ideal case to use. But yeah, definitely this can be used to do that.
Okay, let's stop there and thank Raghu again.